So what I was telling that when you apply a magnetic field along the EG axis, which is let's say the Z axis, so you get a normal hysteresis. But when you apply it perpendicular to it, which is your x-axis, suppose, so if you apply that, so you get a very weird hysteresis loop, and it is called a hard axis hysteresis. So you have a EG axis hysteresis loop, and there is also hard axis. Okay, so always remember the magnetic material will have an EG or hard axis. So EG means it is easy to magnetize along that direction. So the magnetization prefers to stay along that direction, and the hard axis means the magnetization doesn't like that. So in this case, magnetization M prefers to lie along your Z axis, which is your EG axis, but it does not like the X axis, and that's why it is very hard or very difficult to magnetize, and even easy to demagnetize, but very difficult to magnetize along this hard axis. So this is your hard axis. So when you measure the hysteresis loop, you have to be careful. Okay. Okay. So one more thing which I wanted to discuss in the beginning, but I missed that, that's two things. So one is how do you produce magnetic field? Okay. So in magnetism, so two things. I mean, definitely you want to know how you can produce magnetic field so that you can measure the hysteresis or do something, some kind of experiment. So how to produce magnetic field? So of course, you know probably most of the how do you do that? So one is like you take a solenoid, right? So we have a coil where current I is flowing through it. So the length, let's say, will be, this is length of the coil is L, and N is your number of turns. So the magnetic field which is produced at the center will be B, that is mu naught H, which will be equal to mu naught N I by L. Right? This is so what we are assuming here one is that our length L is much greater than D. So D is your diameter. Okay. So if your length of the coil is much larger than D, so you can approximate this equation to this form. So that means you can produce a magnetic field just by flowing a current through a coil. And how can you increase this B field? So you can increase current I, or you can increase N, right? So just keeping the length constant. So if you increase the number of turns, you can increase the magnetic field, and also you can increase the magnetic field by increasing the current I. So which is preferable, or which is consumes less energy? So should I increase N or should I increase I? So if I increase N, why? Okay, yeah. So why do I increase N? Yes, so energy dissipation, that's correct. So that means you always have a joule heating, okay, due to the current which is proportional to I square R, okay. So that means if I increase I by 2 times, so if I want to increase magnetic field twice, I increase I twice, but I increase the joule heating by 4 times. I increase that I square. So that's why it is better to increase the number of turns. So if you want to increase B 2 times, so increase the number of turns twice. So keeping the current constant, so the heat dissipation remains the same. So now what happens? Let's say in this exact. So I take this case. Now, so here it's an empty one. So what I do is I put a iron core inside it. So I introduce an iron core inside it. So what happens? So how much will be B? So B is again it is the same. So instead of mu naught, so I will have mu into H, right? So since I have introduced this iron core, so which has certain magnetization, right? So it has certain magnetization, so which will be given by mu naught H plus mu naught M. Okay. So sometimes you also write it like mu naught H plus J as well. Okay. So all these are vector terms, remember. So J is your magnetic polarization. Also sometimes it is written like this. And mu is your permeability. So that means if I introduce a magnetic material in this coil, so if I take a magnetic material like the iron or steel and I wound a coil around it, I will have for the same current, I actually will produce much more magnetic induction, right? Because now it is proportional to mu permeability, and permeability for iron will be, so this is of the order of 2000, right? Very high. So if I take a high permeability, a material with high permeability, so then I can actually, with the same current and same coil setup, I can produce more field, which I can use for any application. So this is like very similar to your electromagnet, right? So this is the basic principle of an electromagnet. So you will use this to produce magnetic field in an electromagnet. Okay, so there is also another, so solenoid, when we talk about solenoids, so I'll just write down these different, so how do you produce? So one is solenoid, second is Helmholtz coil. You might have seen it in a physics lab already. Then there is, so solenoid can be a normal solenoid or a superconducting. So we are not discussing the superconducting part yet, but we will discuss it next week, the superconducting. Okay. So Helmholtz coil, then you have electromagnet, then you have your permanent magnet. Okay, so electromagnet is basically, so all are some variation of, like you wound a coil and you take, so in this case, most of the time these coils are made up of copper, okay, insulating copper wires. So you take these copper wires and wound it around iron core or some just normal and you get different kinds of so you can produce magnetic field in different ways. So I again want to present something on this, so you can look at the presentation now. So I go to full screen. Yeah. So these are the different ways you can produce magnetic field. So this is what I discussed just now. So this curve basically tells you that if you introduce a iron core, a soft iron core, so with a high permeability, so you can increase, like the red curve what you see here. So the B field is actually increased by a factor of mu naught m. So which is nice. So this is again a Helmholtz coil. So in Helmholtz coil is basically you have your R. So the distance between the coils is exactly equal to the radius of the coil. Okay. So this distance. So here it is already mentioned it is R, but you can say it can be different. Okay. But normally for a Helmholtz coil,
So,
yes.
so we are not able to see the slide. It is only first slide
Sorry.
visible. Sir,
Louder.
only the slide is
Ah.
the part you're explaining is not visible.
The part which is
Sir, actually we are
The
only
part which
able
you
to
were explaining.
see the first slide, which is titled Magnetic Materials Production and Measurement of Magnetic Field, nothing else.
okay.
Now sir, we can see.
Wait. I will just share again. Okay. And your entire screen. Yeah, I understand what is the problem. So now you are able to see the slides, right? Now it is visible?
Yes, sir.
Okay. So what I was, the first few slides were basically what I discussed already. This is what I told. So if you take a high, so material with high permeability, so you can have a higher induction B due to this difference